Quantum entanglement is a phenomenon in quantum mechanics where two or more particles become correlated in such a way that the state of one particle is dependent on the state of the others, regardless of the distance between them. This correlation exists even when the particles are physically separated and can be instantaneous, defying classical notions of causality. The entanglement between particles arises from their wave-like nature, described by quantum wave functions. When two or more particles interact and become entangled, their individual wave functions become interconnected, forming a single, combined wave function that describes the entire system. The key characteristic of quantum entanglement is that the state of a single particle cannot be described independently of the others in the entangled system. Instead, the entire system must be described as a whole. This means that measuring or manipulating one particle's properties instantaneously affects the properties of the other entangled particles, regardless of the distance between them. One famous example of quantum entanglement is the Einstein-Podolsky-Rosen (EPR) paradox. In an EPR experiment, two entangled particles, such as photons, are created in such a way that their properties, such as spin or polarization, become correlated. If one particle's property is measured, the other particle's property will instantaneously collapse into a corresponding value, even if they are far apart. Quantum entanglement has been experimentally verified and plays a crucial role in various areas of quantum physics, including quantum computing, quantum teleportation, and quantum cryptography. It has profound implications for our understanding of the fundamental nature of reality and continues to be a topic of intense research and exploration.